Brandon, whenever you're ready.
Okay. So my capstone is creating software to improve mathematics education. My mentor, Mr. McAlpine, and my faculty mentors, Dr. Reikis and Dr. Kamlodi, I would like to give my thanks to for helping me through this project, along with Mr. Eddie Duffin of Violetville Elementary Middle School for allowing me to go to his after-school program and assess some of his students. Now, before I begin, I'd like to, can all of you read this? I'd like to have a little poll. Imagine that you're a teacher in an algebra classroom and you want to pick out which of these 4 problems best assesses a student's ability to know algebra. And I have 4 questions in front of you, each with a different style, you could say. And I'd like to just have a vote to see maybe which one of you think that the first one is the best way to assess algebra performance. The second? Third? Fourth? So each of these problems actually has a place in a classroom, and they work with different learning styles. And one of the difficulties, my research question first is, how can software be created to effectively facilitate students learning mathematics? And one of the biggest difficulties with this is there are 4 learning styles for different students in a classroom: mastery, understanding, self-expression, and interpersonal interactions. And the 4 questions that I gave you earlier each target one of these learning styles. But it is difficult with software to sometimes target all 4 of these because sometimes a computer can't know who's using it, and it can't know the learning style of who's using it. So it's important to be adaptive to the user, and that's one of the biggest challenges of this capstone. In the end, I created an activity called Algebra Blocks, which helps students to learn algebra by giving them blocks that they can manipulate on the screen with 2 different sides of a scale in order to balance expressions, evaluate expressions, and explore algebra rather than simply be given problems to learn it. I also created a game called Function Apples, in which students gather apples for a basket, with each apple having a function on it, and the students try to get an exact number in order to facilitate their evaluation of functions. The disciplines that I used, software engineering, education, psychology, mathematics, and graphic design, all factored into this project. My primary 2 that I used were software engineering and education, but they all had a role. And education is important because of something called Bloom's taxonomy, where there are 6 levels of a certain activity that gauge how much a child might have to think about an activity. At the bottom of the pyramid, knowledge is things like basic rote memorization, like times tables, or solving an algebra problem, like 2x plus 5 equals 10. At the top is evaluation. This is something like taking a real-world situation and making a judgment call that could be subjective based on what the student thinks is right. Between these 2 levels, there are other levels. For example, application would be something like taking an algebra problem and applying it directly to, say, fish population in response to environmental factors. It is generally better to target a task towards the top of the pyramid to make students actively think more, as opposed to the bottom. But all 6 of these levels are important, and thus it's important in the software to make each of these 6 available to whoever's using it. From software engineering, there are other principles that have to be factored in, mostly regarding usability. An application must be learnable, it must be efficient, it must be memorable, it shouldn't have errors, and users should feel happy to use it. If, say, one of these is missing, maybe it's not memorable, a user might use it once but never use it again, and you didn't really reach out to them. If it's not learnable, then maybe they might just, for the first 5 minutes, be clicking randomly on the screen, not knowing what to do, and then just give up. So by targeting all 5 of these, the software is more likely to make students happier using it. The 5 disciplines all mix together into this concept map here. There's 5 bridging strategies that I used: reasoning through analogies, creating compound concepts, building complex and multi-causal explanations, advancing through checks and balances, and bridging the explanation gap. It might be hard to see, but I'll talk about 2 in particular. The first one is bridging the explanation gap, action gap, which connects education and math, and this is the most important bridging strategy of the project. In educational algebra settings, there are such a thing as algebra blocks, which students can manipulate in order to express certain algebraic expressions on a desk. Say there's an x block, there's a 1 block, and they can put those together to make x plus 1. They can have multiple 1s to make 5x plus 7. They can move them around on their desk, manipulate them, represent multiplication. But there is one limitation in a real-world setting, and that is that variable blocks cannot change their length or size. So there is a limitation in education that I use software engineering to kind of address or fix. Because in software, the size of a block is not static. You can change it based on what the user says or what you say the block should be. So users are able to actually change the length of the blocks to make a variable more like a variable, and thus it helps their cognitive algebra understanding. The other one that I'll talk about is advancing through checks and balances through interface design. And so as part of the education, I wanted to have a kind of scale to represent solving an equation. And there were some interfaces that worked better from a software engineering perspective. There were some that worked better from a graphic design perspective. So I kind of just had to use trial and error to see which one worked best for the users, because each discipline had a different point of view. So I used something from software engineering called agile development. Normally, in the software world, there's waterfall development where you'll analyze your requirements first, then you'll design what you're going to build, then you code it, then you test it. In the testing stage, you don't go back and recode anything. You just go through these 4 steps, and after testing is done, you present your final product, and that's it. This doesn't work so well in user-centered computing because users are all a diverse group of people. You can't exactly predict them, especially not from only what software engineering says. So you have to have rapid prototyping and constant testing. So agile development essentially makes you do all 4 of these steps at the same time. You build a prototype, a week later you test it, you redesign, you recode, you retest, until you get the interface right. And this was essentially advancing through checks and balances because it was mitigating or negotiating the conflicts between software engineering and graphic design in terms of building the interface. When I went to test this program, I went to Violetville Elementary Middle School, and I had groups of 4th graders, 5th graders, and middle school children, all of different mastery level, and I gave them the Algebra Blocks program and created varying lesson plans based on their specific grade level, and was able to kind of diagnose whether this software was able to effectively facilitate their learning of algebra, more so than they might get in a classroom. And unfortunately, I was not able to gather a significant amount of data, but through the lesson plans that I gave, the students' responses to the application were largely positive, and I believe that this is a good step towards the future of education and software and their mixing.
Questions for Brendan? Let's hear from some students.
Yes.
Are the games tough?
No.
Like the
Well,
students?
they had some trouble with the function apples game because the apples were falling too fast at first, so I was able to take that and make them slower later.
So you mentioned that you couldn't change the size of the chunk. I guess you were talking about arrays. Could you speak a little bit about that?
That's more towards real algebra blocks, like physical things that you can hold.
Mm-hmm.
Some teachers use those in classrooms to help students understand what a variable is and how to represent expressions with real blocks. So the idea is that in a computer, you can actually change the size of variable blocks so that x is 2 in one scenario, but x is 5 in another scenario, and it's actually the size of 5 one blocks.
So it's more of a real life limitation, not a
Right.
computing limitation.
Yeah.
Got it. Thank you.
So you mentioned that you built your program from scratch, right?
Yes.
How long did that take?
The first prototype was done in a week, and then I was able to, I didn't test it on elementary school kids at first because I didn't have access, so I gave it to other college students, and they gave me their feedback, and I changed the interface around. And overall, the coding itself is fast. It's just rapid iterations means that it's done throughout a long period of time. Yes.
So do you think, like, for the future, teaching through game design would be more effective than our traditional teaching methods?
I believe it's more engaging to the students to physically be able to manipulate things on the screen that might be able to, overcome physical limitations like blocks being not able to change their lengths.
Can you give me a specific example of activity you were doing and how is it related to the pyramid on your PowerPoint?
So one thing, like the four learning styles, mastery, understanding, interpersonal, and self-expression. For a mastery task, you could tell a student, here's an expression, 5x plus 6, put it on the left side of it, and they would drag x blocks and 1's blocks until they get that expression. If you want them to solve an equation, you can maybe say x squared equals 5x plus 2. You tell them to put an x squared on the left side, a 5x plus 2 on this side, Oh. You can't. There should be blocks. But essentially you would drag blocks into the screen and the equation would balance. And they would solve equations that way. For understanding, you could have them answer a question about how the scale balancing relates to the equality and equation. For self-expression, you could have them build their own equations, give them to other students to try to toggle with the controls, change the variables to try to solve on their own. So there's a variety of tasks. It is essentially solving equations, but the way you apply it to other things can target different learning styles and different